Look at the second slide then. So this is the layout of the microcontroller that we're going to use. There's a couple of different varieties of it. We are going to use a through-hole package, a PDIP, plastic dual inline package. You will see in the datasheet some references to other outlines as well. The small outline IC is one of them. Now, do not get confused, because in the datasheet they're dealing with different package types and they have different capabilities. So one that we use is a Pic 16F84A. So whenever you're looking through the datasheet, just make sure that you're looking at the right thing. So this is the, I've just picked out the picture just for this one and not the small outline IC. As you can see, it's an 18-pin package, pin 1 indicated with the dot there, and we've also got the cutout there, standard on the stuff we've used so far. Now the Pic 16F84A has something that are called ports, and there's two lots of ports. Ports are just groups of pins, or groups of input and output pins, and they get called port A and port B. So if you have a look through all these pins here, in this diagram here, you'll see, for example, RA1 and RA0, they belong to port A. RB7, RB6, these belong to port B. So it's got two ports. These ports are tri-state. That one threw me initially when I started to learn about microcontrollers. Tri-state pins can output low, in other words, like 0 volts or close to it, output high, and then also they can be used as a high impedance input. So there's 3 different states to them. So basically, as an output, you can output a high or low, and then also you can use them as an input. And hopefully you remember that why we might want an input to be high impedance, so it doesn't load the circuit that's providing the signal. So let's just have a look through some of these pins. I've noted down some important points. You'll see pin 4 is the master clear, and as I've noted up here, the horizontal bar above indicates it is an active low reset. That's going to be important. So if, for example, you ignored that and you didn't connect this to anything, so you left it floating, the chip might just keep on resetting itself, because remember, it's going to reset when it's low. Okay, so we've also got this pin, pin 5. This is known as VSS. They don't call it 0 volts, they call it VSS. That is, though, what we're going to connect to our ground rail, 0 volts. It might be worthwhile just remembering that S comes from MOSFET's source, if you remember source, gate and drain. Okay, on the right hand side I'm pointing out that pins 15 and 16, they connect to a clock. So the thing which is going to determine the rate at which this is running, that's going to connect up to 15 and 16. VDD is the positive power supply. Remember I said about drain and source and gate. So on lots of chips like these, you won't actually see like plus V and 0 volts. You'll see VSS and VDD. That's most of the things that we need to cover there. Okay, let's have a look at the next sheet. There's loads of stuff here. I realise this. These ones here are the absolute maximum ratings. All of this, you can't skip it, but let's just point out some particularly important stuff here. The maximum output current that can be sunk by any I/O pin, maximum output current sourced by any I/O pin. Okay, so let's just quickly review sinking and sourcing. When you sink current into an output, the current is going to flow into that pin. It's going to enter the pin, and when you source it, that's like the traditional view for most students, I think, where the output has a current coming out. The source, when you source from a pin, it's going to come out from that output pin and go through down to ground. So you'll notice that the output currents by any I/O pin are limited to 25 milliamps. That's going to be quite important. I frequently find students ignore that and then say maybe they're going to drive like an array of LEDs or something like that, and put the LEDs in parallel, and maybe each LED is pulling 20 milliamps or whatever it happens to be. So don't do that. the maximum current sunk by port A, the total of port A is 80 milliamps. So if you've got multiple pins being used in port A or port B, you've got to total up the currents and make sure that in total the aggregate total is not greater than the maximum current that can be sunk by that port. So you've got individual pin limits, and you've also got port limits. Let's skip through some of that now. I just want to point this thing out here. Okay, this seems a little bit random, but I've included the prices that we often pay for our Pic 16F84As. So I guess we'd probably buy 25 at a time or more. £2.61. Now, if you exceed the power supply voltages, we had a student last year who circuit didn't work, so just kept on turning the voltage up. Just thought, well, maybe it will start working. Obviously, it didn't. Don't do that. They're not throwaway prices. And also, if you apply, like here, voltage on VDD with respect to VSS. So, for example, if you reverse bias it, so you put VDD like minus 4.5 volts because you've put the battery around the wrong way, say, potentially, you've exceeded the absolute maximum rating. So, yeah, you might damage your chip. Now, the chip might not just go up in smoke, probably won't. You might not notice anything wrong with it, but it might perform unexpectedly later, so you really don't want to do that. It'd be a good idea to consider adding a diode, but don't forget that you can have the forward voltage drop of the diode, so silicon diode 0.7 volts. So, for example, if you have like a 4.5 volt battery and you've got silicon diode of 0.7 volts drop, then you've only got 3.8 volts left. That really is significant. I need to impress on you that diode drop is going to be significant later when we look at clock speeds. Okay, let's look at the next slide. I thought this was quite useful from the data sheet. It indicates for test conditions of a 4.5 volt supply what an output low actually means. So if, say, you have a pin configured as an output and you output a low, logic low, false, off, whatever you want to say, it might be 0 volts, but at most it should not be any greater than 0.6 volts. That's the low. The output high, on the other hand, let's say if you've got like a 5 volt battery, you can't expect when you make an output high, you can't expect that same voltage out. So what this is suggesting here, then you should get at least whatever the supply voltage is less 0.7 volts. So say, for example, if you've got a 5 volt battery, then you might expect at least 4.3 out when, when you've got a logic high. That's for all ports there, including these special ones. Okay. Moving on then, let's have a look at this stuff. Yeah, so the Pic 16F84A is a reduced instruction set microcontroller. There's only 35 single word instructions to learn. We'll come to those later, and you don't even need to learn all of those, not for the A level. This thing, though, really causes people lots of issues. I had lots of people last year who were suggesting to me that they thought they could get their microcontroller to run at 20 megahertz, and fair enough, it does say that, doesn't it? However, you won't be able to do that. We don't use the microcontroller, the version that will actually run at that speed. If you have a look, if you remember, let's just go back a moment. I said we used the Pic 16F84A04. Let's go back to the slide. The Pic 16F84A04. We can get it to run at 4 megahertz. Now, importantly, we can get it to run at 4 megahertz if we have a supply voltage between 4 volts and 5.5 volts. So, like I was saying earlier, if you have 3AA batteries, say, and they are maybe 1.5 volts, maybe they're not, maybe they're 1.2 volts each, and then you have a diode as well, which is going to drop 0.7 volts, you're going to be less than 4 volts, you may not get the 4 megahertz frequency. I'm not saying you won't, but you may not because you're not working within the manufacturer's parameters. So that's Pic 16F84A. So where do they get this 20 megahertz? Well, if you have a look over here, look, there's some different figures here. Look, Pic 16F84A04. Okay, so I presume that's the low voltage one, although I don't know that's a fact. So yeah, you can get 10 megahertz, you can get 4 megahertz down to 2 volts, but we don't use that one. Okay, so ignore that one. This is one we use. You will not get 20 megahertz. Okay, so this ran a bit. I said this last sentence is very useful. Let's read it in RC mode, resistor capacitor mode. This is the oscillator, the timing thing. Okay, this pin outputs the clock out, which has 1/4 of the frequency of OSC1. Now this is the main thing that I wanted to get across. It denotes the instruction cycle rate. So for example, if you've got an RC network that gives you a frequency, input clock frequency of 4 megahertz, that's then going to be quartered. So 4 megahertz divided by 4, 1/4 of it, is going to be 1 megahertz. So that's the instruction cycle rate. So 1 megahertz, 1 million clock cycles a second. Okay, let's carry on reading. So why might adding the reverse bias protection diode be a problem? Well, hopefully you understand now that you might find that you have dropped too much voltage and you're not within this 4 volts to 5.5 volts range. Okay, looking through this, table 1.1, actually very, very useful. Don't forget that this is for the Pic 16F84A pinout description. There might be another table in the datasheet for the other form factors. So some inputs have Schmidt triggers. If you look through it, each one of these is telling you which pin we're talking about. Remember RB1, RB0, these are port B, so these are port A, so you can see that we've got 5 pins in port L, 5 inputs or outputs in port A, and then 8 from 0 to 7 in port B. And you'll see that some of these, if you have a look at buffer type, you'll see some of these have Schmidt triggers. The reason why I'm raising this is because last year I had some students talking about adding Schmidt triggers, as a discrete thing to tidy up input onto some pins, and I pointed out to them that this microcontroller actually has Schmidt triggers for the very purpose that they were after. So yeah, you do need to check. If you want a Schmidt trigger input, then there probably is one available here. Let's have a look through. So master clear, yeah, we know that. Okay, just looking through. TTL logic, you need to Google TTL logic to find out about that. RB0 has a particularly important function. This thing here, it can be selected as an external interrupt pin. You need to learn about that in the for the exam and also for your coursework, but we'll come to that later. This thing is what we mentioned on the previous slide, that the instruction cycle rate is the frequency of the oscillator divided by 4. If you ever decide to use RA4, and I would avoid it unless you have to understand it's an open drain output. So I copied these ones from the internet just to hopefully explain. Okay, so looks like it's got a MOSFET there. So this is like, if this were the microcontroller, and hopefully you can see that we're actually going to sink current into the output. And so when the output goes high, then no current will flow because there will be no potential difference, or too small a potential difference between here and the pin. And when the output goes low, so traditionally you'd think, well, low, it will go off, but actually no, then you've got potential difference, so then you could actually have current sunk in there. One thing to really stress, because I've seen students do it now, is that you must have a current limiting resistor, or must have some sort of resistive load here, because when you think about it, you've just got a MOSFET here and you've got gate, drain and source. If you don't have any resistance of current, then basically, and let's say if you just tied this to the power rail, you just have a straight, virtually a straight short. It's just going to be limited by RDS on of the MOSFET. Not a good thing. Yeah, I point this out. Port B, does it say it here somewhere? Yeah. Port B can be software programmed for internal weak pull-up on all inputs. So you might just want to bear in mind that, like if you were doing systems control last year, you probably remember that we can't have floating inputs. So you normally use a pull-up or a pull-down resistor. You don't actually, with the Pic 16F84A, you've got the option if you want to enable an internal weak pull-up. So instead of having an external physical resistor, you can enable it in software instead. So yeah, if you want to, you can do that. This table, what have I said? Useful information about logic level thresholds. So what have we got? Yeah, okay, so this is for inputs, isn't it? Yeah, input low voltage. So what is regarded as an input low? So it depends on which type of port you're using. Let's just say it's an I/O port and not a SMIT trigger port. An I/O port would regard anything between VSS, 0 volts in our case, and 0.8 volts to be low, assuming that your supply voltage was between 4.5 and 5.5 volts. Slightly different for SMIT triggers, and then the high, logic high, will be, if it's a TTL input, will be between 2 volts and the supply voltage. So for example, if you gave it 1.9 volts, that would be somewhere in between logic low and logic high, so you wouldn't want that. If you want to make sure it's a low, say you could give it 0.5 volts, that would be regarded as low because it's between VSS and 0.8. If you want a logic high and say you gave it 3 volts, that would be regarded as high because it's between 2 volts and VDD, the supply voltage. Okay, no doubt there's some more stuff in there, but I'll just skip on, otherwise this video will go on forever. Oh, loads of stuff here. Types of oscillators, yeah, we've got different things we could do. As a school, we tend not to use these crystal oscillators. I've got some at home. If you use a crystal oscillator, then you use a couple of capacitors there. We tend at school, because they're just convenient, to use a ceramic resonator. We've got some 4 megahertz ceramic resonator. And remember, if you have 4 megahertz, then it's going to be divided by 4, so it'd be 1 megahertz. So instruction cycle is going to be 1 million times a second, which is actually quite convenient when you do some calculations later. So if you use this package, it's basically it's like a crystal with the capacitors in there. When you use Circuit Wizard, there isn't this component, which is really annoying, but you'll come to that. In fact, I don't think there's a crystal in there either. Might be worthwhile reading through this. I have copied it for good reasons. I thought it was useful. These links as well, I recommend them for having a look. One point I wanted to make is that I think somewhere I possibly read about it. Oh, there we go. RC oscillator offers additional savings during purchase, but you know, don't choose an RC oscillator just because, which is just a resistor and capacitor, just because you think it's going to save money. Because look, we're only paying 20p for the ceramic resonators anyway, so I'm really not bothered. Just ceramic resonators if you find it convenient. If you're using Circuit Wizard, as I say, it's got a limited choice of components. So one thing it's also missing is a ceramic resonator. So if you do a circuit diagram in Circuit Wizard and you want a ceramic resonator, I just went for this 3-pin single inline connector instead. If you don't have a ceramic resonator or a crystal, or you just want to be really cheapskate, and I've done it before and it works perfectly fine, I just use a resistor and capacitor. and then there's a table somewhere, it's probably coming up soon, showing you about how to calculate what frequency that's going to give you. Anyway, might be some useful stuff there. More stuff about using a resistor and capacitor as the oscillator. Yeah, okay, so it's giving you some recommended values that you might use there. Yeah, so follow their recommendations. If you're wondering why I put that there, I think it's just cheapskate, really, just using the resistor and capacitor, but if you want to, you can do. Okay. You can read that if you want. I don't think there's anything super important. If you still set your heart on using a resistor and capacitor, maybe you're doing it at home, you don't have the part. Here's some charts from the datasheet to work out what frequency, but bearing in mind there's quite wide tolerance on the parts, you're not going to get exact frequencies, but anyway. So let's have a quick look. Okay, frequency oscillator is going to, in this graph, is going to depend on the supply voltage. And they're saying here that if you have a capacitor of 22 picofarads and you keep the temperature constant 25 degrees, these are the different frequencies that you're going to experience according to what your resistor is. Okay, so hopefully you can interpret that. I'm not going to go through in detail. That's with a 100 picofarad capacitor. That's 300 picofarad. It's not going to give you a precise frequency. Okay, it will not. But you know, you're probably not going to do something time sensitive anyway. Okay, if you remember, slide 11, we'll go back to that in a moment. If you remember master clear, so you need to do something about master clear, because if you don't, nothing's going to work. So if you don't, this is showing a possible way to have a reset switch. If you don't want to have a reset switch, just make that bold here. If you don't want to have a reset switch, you could just pull the reset pin straight up to the supply voltage. Nothing wrong with that. However, if you do that, and even if you don't want to have a reset switch, maybe you want to just chuck in a resistor for like less than a penny between pin 4 and the supply rail. The reason doing that is maybe later on you fancy just adding a jumper wire or something, so you during testing, so you can just pull that pin down to ground, and if you don't have the resistor, then that might not be so convenient. It's not too big a issue really. If you want to use the reset pin, then you probably want to debounce it. So here's a possible circuit. I think we've gone through something similar before. Okay, these are all the instructions that are available, not all the ones that you need to learn about. We're going to go through all this in detail. Okay, so I don't really want to do it now. It's in the data sheet. This is just like a summary table. If you find this in the data sheet, can't remember what page it's on, find it in data sheet, like the next couple of pages, I think afterwards, it gives you much more detail about each command. However, you still want to read some of this stuff. I can't remember whether, maybe it's not there, but there is some very useful stuff elsewhere on this page. Okay, so a couple of years ago, most students were removing their Pic 16F84A chips from the circuit each time they wanted to program them, using a programmer that was attached to a computer, then removing the chip from the programmer, and pins were getting bent up and it was causing them a problem. And then so what I did last year was introduce a Pic Kit 3, which is an in-circuit serial programmer. And so what that gave everyone was the ability to leave the chip in the circuit boards that they were making and then program it in circuit, yeah, in place. It's considerably more convenient, a lot better. You're not having to yank the chip in and out all the time. It's just wholly better. Everything about it is better. Okay, so I strongly recommend, pretty much insist, that you give it a go. Okay, that you're going to include an ICSP header in your circuit. It's so easy to do as well. Okay, this page gives you loads of information about it. On the data sheet, I think, which we looked at earlier, there was something about RP6 and RP7 hidden in here. I initially, when I first got Pic kit, I found this a little bit buried. Did find it in the end, though, that these two pins are actually the serial programming clock and the serial programming data. And then so programming clock, PGC, and programming data, PGD, that's what those are referring to. So for example, I think this drawing is terrible here, but pin 1 of the Pic kit should then go to master clear. Pin 2 of the Pic kit, by the way, that arrow, the triangle there, is referring to pin 1, and then so then pin 2 of the Pic kit will be going to the power supply, etc. So that's the way it gets wired up. I think there are actually 6 pins on the Pic kit. I think the last pin, pin 6, is for low voltage programming, which we don't use. Let's carry on down. We're almost, well, we're getting close to it. You can, if you want, you can breadboard it. Breadboard your circuits. It would be very nice though if you could come up with a PCB. I mean, really nice. Also, we've got various competitions and things regionally that you could enter your projects for if you say make a more permanent version and possibly make a case as well. So I encourage it. It's a good skill anyway. So look, just as an example, I made didn't make it, I designed a circuit in Circuit Wizard for this, just to show you that it's probably possible. I haven't tested it, okay? And don't copy it and claim it's your own. I don't mind you copying it, like to use it to test something, but don't copy it and then try and submit it as your coursework, because yeah, you won't get away with that. There is no Pic 16F84A in Circuit Wizard, so what I do, I just drag in a DIP package, an 18-pin DIP package. So it means you can't do any simulations in Circuit Wizard. I mentioned earlier that there's no ceramic resonator, so I just use a 3-pin single inline connector. The only reason why I used that with switch was because I wanted to use a slide switch there, and that one converted automatically into that. I've included a diode there, and you'll probably notice I've got a 6 volt, which normally we don't use, but of course 6 volts with a diode drop of 0.7 volts, that will give me 5.3, and the timings we looked at earlier was for 4.5 to 5.5, if I remember correctly. So that would be my reasoning. I'm just looking through now. Can't remember what the pinouts are on these, so we'd have to check. Okay, but anyway, yeah, a couple of these pins, I believe they're probably the programming data and the clock. In fact, they are. Let's see that. Why do you think I put LEDs on them? Well, to me, I find it quite useful that whilst the Pic kit's programming the chip, I can actually see a little bit of flashing. I mean, the flashing I can't interpret, but I can see there's activity on those lines. I find it quite useful. As I say, I haven't built this circuit, but I've built lots of other Pic kit circuits or Pic 16F84A circuits, which have used Pic kit headers. So I have some experience of it, and this one might not be absolutely right. I haven't double checked it, did this quickly, but maybe you can, if you can see an error, point it out. We can always update it. Equally, haven't made this one, and this one's unfinished. I just started off just to show you roughly what the layout of a strip board could possibly be. Not definitely, but possibly. So if you look, okay, so the power from the battery go through a diode, so then this rail here, the lower of these two here, that's my positive supply, and then that's my ground, so then I extend my ground there and take my ground there as well, so that's my ground. This is header connector for LEDs, so yep, and then all these are the resistors for the LEDs. I'm using 3 of the outputs there, which is RB1, RB2, RB3. Haven't used RB0 because that's the external interrupts. I might use that for something else. And then if I wanted, say, to use RB5 and RB4, I could take some wires around from here. And anyway, it's just like showing you a possible sort of setup. This would be for the Pic kit. Yeah, as another good thing to note is that I've added, and this would be like one of the first things I would do. So along with the pin header, and then the diode, I've then got a resistor and a power on LED, just to show me when the power's on, when the power's connected. It's really useful because then if later on you accidentally short out the connections somewhere on the board, then your power on LED won't light. Yeah, so that's really incredibly useful. Moving on. Oh, we're almost there now. Look, if you want more information, just Google search Pic 16F84A. Should come up with a link on the Microchip website, and this is the datasheet you should find. Do look at the table of contents. That's the way I navigate around. We're going to be using MPLAB X IDE. Once again, you can just Google it. The current link, last time I looked, was there. If you're using Windows, I've also used it on Linux, perfectly fine, it's good. And if you're using Windows though, yeah, that was the link that I found at that time. Oh, that's it. Okay, so yeah, basically that's a run through of some stuff that I found that was useful. It's not entirely comprehensive. It may include the occasional errors. If it includes anything significant, I'll either completely update it, maybe scrap this video, or add a comment in that hopefully people will read. But yeah, I will make this available to you so you can use this as a resource, and then you can refer back to it. And I really want you to be using this to then guide you and encourage you to read the data sheet, because it's a data sheet which is the reference. What I'm saying is just my interpretation of some things. Okay, so anyway, that's it. I'll stop things there.